All right, now we'll talk about another data structure for priority queues. The abstract type here is called min queue, and it's a priority queue in which, as for all priority queues, we can insert an arbitrary item, but we can only delete the item which is the minimum one. And so we can implement this. There's more than one way to implement that. I'm going to show you one way, which is what I call the array implementation. We develop a data structure which is simultaneously an array and which is also a binary tree. Now, one way to show these at the same time, here are the items from 1 to 9, and these items, I can imagine them moving a little bit so that I can spread them out and make a binary tree where the links are the green lines. Now you notice that the child is always greater than or equal to the parent. So this is what's called heap order. Heap order means the child value is greater than or equal to the parent value. All right, now that's because it's a min tree. If it were a max tree, the child value would be less than or equal to the parent value. So this is the shape of the tree. Each item has 2 children unless it's farther down. And if you want to notice, the children of 1 are in positions 2 and 3. The children of 2 are in positions 4 and 5. The children of 3 are in positions 6 and 7, and the children of 4 are in positions 8 or 9. Now there's a formula to that, and what is that formula? Well, I'm going to have to erase this part in order to write that here. The child of the children of the item in position I of the array in position I are the values in position 2I and 2I plus 1. So you see, if I is 1, then in position 1 the children are in positions 2 and 3 and so forth. Now, the parent of AJ is AJ over 2, where you use truncated division. So if I want to know the parent of 5, 5 divided by 2 is 2.5. We truncate down to 2, so the parent of H is D, the item in position 2. All right, now, in a heap, you have to do insertion, deletion, and when you delete, you have to delete the minimum one. So let's look at the delete min operator here. The first step is to return the value of the minimum item. So that means that the minimum item in this situation would be A. So that will be the value returned by the delete min. Now, we then move the last item up to position 1, to the root. Now the last item is unlikely to be the smallest item, which means that this particular tree is now out of heap order. So what has happened here is this position has been deleted from the min queue. We now have a value G in the array at that position. Now what you do here is you bubble down. You bubble down recursively until it's stabilized. Look at these two children, D and N. The smaller of them is D. So what you do is you switch, you exchange the smaller, the item with the smaller of its two children. And so now this position becomes G, and this position becomes D. Now we still bubble down here. We look at its two children, and we say, is there anything smaller than G? Well, H is not, but E is smaller than G. So we switch here, G, E, and now we have this position here. This is now a G, and this becomes E here. Now we're not done because we now have to bubble down one more time. We have to look at its children and say, is there anything less than G? Well, this child doesn't exist anymore, but F is less than G. Therefore, we have to put G there and move F to this position. Now, if we look at the structure of the tree as it now exists, let me make these a little clearer here. This is F, this is G, this position is now D, E, and this position is D. Now, the items are now in min-heap order. Once again, it's been restored. And it took logarithmic time, no more than log n time, to do this bubble down. Now we'll consider how to insert into a min-heap. We'll start with the min-heap we had after the last deletion. There are now only 8 elements. And suppose we're going to insert, we want to insert B. Now, we're allowed to put a new item in only one place because the array has to be extended contiguously that way. We can't go skipping over things, which means that the E, the new thing B, has to be placed there. And so there it is. But you can see right away that there's a problem. The binary tree is no longer in heap order because the rule has to be that the child is greater than or equal to the parent. And it's not. This child is less than the parent F. So the bubble up means that the new item continually swaps with its parent until it's in the right position. So the first thing we notice is that B swaps with its parent F. So B goes here and F goes here. Now we continue to bubble up, checking against its parent, which is E. Now that E is larger than B, so we again exchange. And now B looks at its new parent, D, and it's larger than that, so it exchanges again. And so heap order has been restored. Now what happens here up here is we can see that these values have been changed. This is now an E. No, this is B, I'm sorry. This is a B. This is D. This is E. And this is F. And now heap order is restored, and the smallest item, the minimum item, is at the root as it's supposed to be.